All right, so let me briefly explain what this presentation is not. So you will not learn about the latest CFI bypass here. You will not learn very technical, extremely difficult to comprehend concepts. This is going to be a very straightforward presentation, but we will be learning very cool techniques that you can almost take with you instantly and exploit a good portion of systems if you spend the time to slowly wade through the junk that you see. And of course, just to caveat this, there will not be actual demos in this sort of talk. And the reason for this is that some of it is currently under embargo. It's a bit iffy if I present it, so I will not present the actual findings, but I will present the abstract findings with concrete instantiations by other researchers. But rest assured that these classes of bugs exist, and don't kill me if there's no demo. So really what this presentation is about is really attacking the complexity of software, because software engineers have to deal with complexity every day. And how they deal with complexity is they rely on dependencies, they rely on abstractions of functionality that are given to them by the operating system or libraries. And they don't really understand what's going on under the hood, because no one has time to actually work on everything and understand everything. And because of this complexity, like often the easiest way is actually not the right way. And if you take the easy way out, what is going to happen is that you would miss out on certain security boundaries, and you may end up causing your application to have a bug, or in a serious case, a local privilege escalation. So what kind of bugs am I actually talking about here? So the bugs I'm talking about here is the kind where you're like, okay, this is actually a bug, wow. So I'm sure some of you may have heard of this bug where if you have a Razer device, you plug it into a system, you do a bunch of tricks, and then it gives you system privileges. So if you're not familiar with this, let me just play a short video, maybe it's like a minute, and I'll just narrate to you what's happening. So let's say you have sort of physical access to the device, you have a Razer keyboard or Razer mouse on you, and you plug the USB in. What can you do with it? Well, firstly, you'll try to install the drivers, and of course, it'll install this bloatware called Razer Synapse. They're not sponsored by Razer here, I hope. So what actually happened was that you can actually change the install location, and using that file explorer prompt, you can actually run command prompt. And this installation has to be privileged, right? Because you're writing to device drivers, you're changing program files. And as you can see here, you are able to pop a root command prompt or system command prompt just from the installation prompt. And all you needed was a Razer device on you, plug it into the device, plug it into your machine, and then all you get is it will try to install the drivers, and this happens. So this is the kind of nonsense that we are looking at, right? The edge cases that no one thinks of, but it's really important to raise, especially since this is not something that you see in CTFs. This is not something that you see definitely not academic research. Like this is not very interesting from an academic point of view. It's not very interesting from a CTF point of view even, but it is a security issue that you should be aware of. So maybe I can poll the audience here, and maybe I can ask some of you, what do you think would be an appropriate fix for this? Anyone can answer. You can type in the chat as well. So I think some of you have said things that will, yeah, so maybe only allowing the admin to install, right? So that's one of the things you can do. But how about if you buy a new mouse and you want to use it, right? It impacts user experience. And one way you can do it is that, hey, only a portion of the installation process is run as admin, and you need to escalate privileges. Like you need to use the mouse, but you don't need to use synapse. That's like mutually exclusive. So yeah, I will not speak about the other option, just in case Razer wants to sponsor this, or Razer wants to hire any of us here. Yeah, test on your friend's computer first. I think that's a legitimate way of fixing it to see if there's a bug there. But let's see what Razer did. We saw the cause of the bug was that they could actually change the file location to install the device program software. So how they disabled this security bug from popping up is that they completely prevented the prompt from even occurring by preventing you from changing your install location. So this effectively fixes the issue, because if you can't open File Explorer, then you can't open command prompt. It's a great way to solve the problem. So if you can't click on it, doesn't exist. And of course, you may be like thinking, like, this is insane, right? But it is a security issue. And sometimes a lot of CVEs are lame, and there's some super ridiculous tactics behind it. But you as a security researcher, or maybe security enthusiast, or whatever you want to claim yourself as, you should be able to spot them. And of course, you don't encounter these in CTFs, hence the sharing today. So let's dig a bit deeper into what I really want to talk about, which is the installation process. So I'm sure everyone knows how to install a program. You download the program, you double click it, you just keep clicking next until you're done, and then you click finish. Right? That's the end-to-end process of installing. But do you really understand what's going on underneath the hood? The answer is no, because A, it's not documented anywhere. It's actually an undocumented process of how MSI exec works. So no one really knows except the people at Microsoft. And if you want to reverse it, it's something we can do in your free time. And there's really only like one open source tool that builds the installation packages, which is the Wix toolset. And what this actually means for people who develop software is that no one really knows how installation works. And that's where a lot of bugs come into play. And if you think about the entire installation process, it's a huge, huge pain, because when you want to install software, you need to be able to write to a lot of places. You need privilege, right? You need to install drivers, you need to do a lot of nonsense. You need to write to the program files. So it being a privileged application is already, it is a vector in which it becomes interesting, because this becomes a target for privilege escalation, in particular, local privilege escalation. Imagine a process that is unprivileged. You can take the opportunity that this installation is happening and raise your privileges to anti-authority system, for example. And of course, when we continue to think about this process, the other things that happen here is that you're writing files, you're reading, maybe you're executing more other executables to install your subcomponents, and you need to extract those components, for example. So there's a lot of file writing, file reading, loading of executables going on, and all of these things can be problems, right? Firstly, it needs to make sure that, the directories that I'm saving the files to, those are safe. No low privileged process or user can actually write to it or read to it. And making sure that all of these directories have the appropriate permissions at every single time is extremely difficult. And this is another opportunity for local privilege escalation as well, because in this time you get possibly a privilege write or privilege read. And lastly, there is a need, of course. Let's say it's installing some subcomponent. If you install nmap, you will be prompted to install npcat. You don't really know why you need to use it, but you just install it anyway. But the point is that there's the decompression of all these artifacts that will be installed later. And one thing you can think about is, are those artifacts the same artifacts that came out when it was decompressed, right? This becomes a race condition or time of check to time of use abuse. So the entire process of installation is like a landmine, right? Like any step that goes wrong is like, whoops, I'm gone now. And when I talk about privilege here, what I mean by privilege is not the normal kind of privilege, but like the privilege that we have in computers, which is the root privilege, the root user, or the NT authority system, not the work kind of privilege. So this is the kind of privilege that we are talking about here. So going back to the installation example, we'll first talk about how installation so broadly works, right? So when you want to install software, you first have to download it, right? The software doesn't come from the sky, it comes from the internet. So you go on the internet, you download the exe file or whatever installation package that exists on that platform, and you drop it into your downloads folder, right? Then you double click it, and then it runs, and then you install the software. Of course, more things are happening in the background. For example, let's say this setup is actually a custom executable. I may start to load some DLLs from maybe the native OS that it needs to run the executable. So if you use this very handy tool, which you should be familiar with, hopefully in the InfoSec journey, if you use Process Monitor, you'll be able to keep track of what it is exactly doing at every single point of time, the kind of API calls it's making. For example, in this case, it's actually trying to load the WAL64 DLL and WAL64 WinDLL, etc., etc. So it needs to load that DLL, which is like a dynamically linked library, so that it's able to call upon the functions that are provided by those libraries. So in the case where the executable cannot find the DLL, then it becomes interesting because it will really try to find the DLL. Like it will try very, very hard to find it. So it'll look, if you try to run it without the DLL, for example, being provided, or let's say inadvertently, some core functionality of the app that is not provided by the actual programmer needs some DLL, then it will try to look all over your file system to find that DLL that it needs. Sometimes this is core to the functionality of the app, and sometimes it isn't. So when it isn't core to the functionality of the app, what will happen is that most programmers will completely miss this, and they won't actually find that, oh, this thing needs this DLL. But let's say in this case, it isn't core to the application. We find that, oh, it's actually trying to load this DLL, but there's no error message that's being shown in the application. And we see that it actually loads the DLL from numerous numbers of places, like even places which shouldn't be looking, like for example, tries to look in some other directories. And let's briefly explain where DLLs are being loaded. So DLLs live in many different places, and so there must be sort of like a rule for which we load these DLLs so that we are able to find the correct ones. So where do they come from? And we can break it down into basically 6 different categories. So the first one is the obvious one, right? Let's say you install Adobe Photoshop and you have a shortcut to Adobe Photoshop in your desktop. Like when you double click on that shortcut, you don't want it to load DLLs from your desktop. You want it to load from the actual installation path. So The first one where they get loaded from is from directory where the application is. In this case, it says loaded, but because it's a shortcut to the program files, then it's actually loaded from the program files. So that's the first point of contact. And later on, if it isn't found in the actual application directory, then it will try to look for in obvious places, right? The system directory, for example, let's say it's a core system DLL. In this case, system directory means system32. And the 16-bit system directory in step 3 is system without 32. Of course, there is the 32-bit version of the system directory called syswal64, which is Windows on Windows 64. So fun fact. So of course, after looking through all the system directories, it will look through the Windows directory, which is Z Windows, and then finally look at the current directory. So in this case, for example, the desktop. And after it exhausts all these directories, it will try to look for it in the path environment variable. Of course, we're not going to talk about the last segment today. It's an entire topic in itself, the path environment variable. But know that this is the DLL load order. So in this example app, where we try to load a DLL that does not exist, we see that, hey, it starts from the application directory where it's installed. Then it looks at the system directories, the Windows directory, and then the current directory where we are running the application, and then finally through the path. And what we're interested in when we download installer and then we run it is really the current directory, because we're running it from the downloads folder, and the downloads folder here is the current directory. And that's a directory that we can easily change. So how would we want to plant a DLL into a downloads directory? So this can be really quite simple. If you're able to redirect a user to any web page, so this might take a bit of like social engineering, phishing kind of thing, but as long as you're able to get them to navigate to a single web page by providing a header that's like content disposition attachment, you're able to force them to download the DLL. So once you get them to download the DLL, they may or may not know it, depending on how aware they are. But if they're not aware and your malicious DLL matches the missing DLL in the installer later, what you're able to do is that when the installer is downloaded and then executed, what it will do is that it will load that malicious DLL, and then it will run whatever binary code that's in the malicious DLL. So just a sort of a brief overview of what's happening. When you load the DLL, it goes into DLL main, and which is like your main in C. And essentially, you can define any sort of functionality there, and including a reverse shell, or connect back shell, which is a reverse shell, or a listening shell, any kind of shell that you want. So this is how you get arbitrary code execution in this case. And you might be thinking that this is like a very ridiculous scenario, like this can get a CVE. Turns out, yes. In fact, it turns out that it's a pretty popular product. It's called Firefox. So Firefox used to have this vulnerability where, and they have their own custom setup exe. They don't use MSI. They use their own installer package. So they actually needed to load a bcrypt DLL. Unfortunately, that's not found in at that point of time the system directories or any of the other directories, and it wasn't part of the core functionality of the application. So it wasn't caught in the process. So what happened when you double-clicked it was that it will try to load that DLL. It fails to load the DLL most of the time, and usually that's safe. But if you just happen to have a bcrypt DLL that is malicious on your downloads directory, then you get pawned. So yes, this is a real vulnerability, and you can get a CVE out of this. So something to look for in the future. And this is not isolated to Windows. You can find this on Linux. You can even find this on Mac. The associated vulnerability class is called dilip injection. On Mac, it's a bit trickier. So because they actually specify which directory the dynamic libraries are loaded from. But if you can modify that directory, this actually happened in quite a big product. And if you can modify that directory, essentially you can control the code or the application. So this is a real vulnerability, and it's not something that you see often in CTFs, in fact, never. But this is important to know and important to check if you're actually looking at real software. So talking more about the installer, and sort of a bit of a tangent here. So let's say you got the installer running and it's all great, right? There you don't have any missing DLLs, you're a solid app like installer. But as an installer, you need to invoke some other components. Maybe, as I mentioned, a subcomponent, maybe a post-install script, right? Maybe to send the logs over to a for debugging purposes. So any application that the installer touches, because the installer itself is privileged, any other application also becomes privileged. So things to look out for are like, for example, if you use process monitor, you can look for load image events, and that's indicative of another process being loaded by the installer. Another thing to look out for is any kind of scripts that are run before or after the installation. This is very common in macOS systems, for example. And when you install something or when you update something, updating is pretty much equivalent to a form of installing, because to update, you need to install something. And that presents an opportunity to actually have a local privilege escalation. So any part of installing is quite terrible. And of course, I talked a lot about like, oh, the installer needs to run something, but that something needs to exist somewhere in the file system. So let's say you decompress this artifact that you want to install. For example, this is the installer for some .NET library, right? And this needs to go somewhere, right? Obviously, it doesn't go in the trash. It goes somewhere else. It goes to somewhere that's writable. So maybe like the first thing a developer can think of is, hey, I know one place that's definitely writable, confirm writable. So is this a good choice of where this thing should reside? Let me ask the clever and omnipotent audience. So do you think this is a good place to save files to? Looks good. No, please. So why not? So we have a mix of responses from the audience. So some are like, yeah. All right, no. So the answer is no. This is probably not the right place for it to go. So it's sort of a measured no. Sometimes this is correct with, you can do this correctly, but you may not be able to do this correctly always. The straightforward way of doing it, for example, just dumping the application into /temp without modifying any permissions, is going to be terrible, because what happens is that I'll explain later in the attack scenario, this application or this binary becomes writable as well. And in fact, this broadly extends to any place that is world writable. And this is really an anti-pattern, because anything that you put in any world writable folder is essentially a nightmare. Any low privilege process or user can overwrite it, and you don't really know what happens next. So sort of to put the attack scenario in a more concrete manner. So let's say you have a privileged application. For example, this is a privileged application, like an installer, and you need to install this other subcomponent. So you extract it into Windows 10. So this comes out, right? Everything looks good, except that it's writable. And see Windows 10 as like the more writable place in Windows. And you're an adversary, Maybe you're not an adversary, but there is an adversary. This adversary is a low privilege user on the same machine. And what he does is that he changes the executable with its own malicious executable. You can tell it's malicious because it's yellow. So after this, the privileged application becomes sort of like confused deputy. It's essentially it doesn't know that you changed, or at least someone changed the application, and they're like, hey, I need to install this. Let's go for it, man. So they run that executable with high privileges, and the adversary gets to escalate privileges. This happens more often than you think. So an example of this is in this software, private internet access, which is a VPN application. So what it allows is for low privilege users to update the application. They have a role writable update folder, which is useful because this allows low privilege users to update the application. But what the low privilege user can also do is that they can also create files in this update folder. So in the process of updating, maybe the update process needs to load some DLL. The low privilege user can actually create the DLL first and then lock that DLL from being overwritten. How do they do that? It's as simple as opening a file handler. You can do it in PowerShell. And once you prevent it from being deleted, let's say you trigger the update process, it tries to download the updater. And of course, it isn't able to override the malicious DLL, but it still updates it anyway. And after that, what happens after the update finishes? Because the update process needs privilege access, the privileges of the low privilege user is escalated through the malicious DLL. And you can read more about it here. Maybe I'll share the slides later. So that was one example of like very subtle, like of a bug that can happen. Something where a race condition where the attacker modifies the application that is in a role writable folder before the installer is able to execute it. But there are also more subtle bugs that can happen in this domain. So on macOS applications, it's very common to see pre-install scripts and post-install scripts, which are also executed as privileged applications. And those are typically like shell commands or a shell script that does cleanup, logging, etc. And these applications may try to log it to a temporary log file. Of course, we have seen that this is a terrible choice for a log file. But how would you exploit this kind of bug? What would you do to sort of escalate your privileges in some way? Any thoughts from the audience? So this may be something that you may not have seen before. So let's say in this case, the log file doesn't exist in the first place, right? Maybe you can plant something there that redirects the flow of traffic to another file. So what you can do is essentially, if your log file, you create a symlink to something like /etc password. You can actually completely redirect whatever that was in front into that more protected file, for example, /etc password, and then you can change the contents of /etc password. Of course, in this case, this is not like a full privilege escalation in the fact that you can get a root shell after this, but you're able to modify and eventually even break files in some case, causing a denial of service. So punting files into, or at least writing files into a temporary directory is probably not a good idea because of bad file permissions. There's even more bad things that can happen. So if you look at this, the same scenario, right? You have your post pre-install script that's privileged, and they're trying to zip up the logs, right? And then send it over to for just for analysis to make sure that everyone is installing it correctly. And there are actually a couple of things that can go wrong here. Maybe if anyone can see it, maybe they can try to guess what could happen. Yeah, 755 is one of the things that you can exploit here. So if the logs.zip is, for example, in a sort of controllable place, like a temp directory, you change that into a sort of maybe a hard link, then maybe you can read the contents of the logs. So that's one thing you can possibly do. So that's a race condition that you can sort of exploit, like remove the original logs.zip and then place something else over there. So that's one of the issues. But the other more subtle issue is actually with zipping, because this zip has a very special property that it will decide to say, hey, if you pass me a symlink, you know what I'll do? I will actually, instead of copying that symlink, I'll read the contents of that symlink and put it into my zip file. Because, you know, just in case they cannot access the file in the future, right? Because they use Windows, and Windows is awesome. So in this case, how you will exploit such an issue is that you will plant symlinks into /temp/logs that points to, for example, @c shadow or whatever. And then when this zip command runs, and then the permissions of this zip command is changed, what will happen is that anyone can read the secret file. Of course, to exploit this, you can also look at reading SSH keys or similar. So yeah, this is terrible, but it happens. Things to look out for. So you may be thinking, oh, no, this is just happening during installing. You know, if I uninstall, it's safe, right? So what I spoke about in the top half of this presentation applies to not just installation, but also uninstallation as well. And you may be thinking, wow, installing and uninstalling, well, they both suck. So what can I actually do here? And maybe in the case that the user decides to choose not to install or choose not to uninstall, maybe they're doing nothing, maybe you can't do anything anymore, right? If I don't install, and if I don't uninstall, I'm 100% safe. Well, this is not actually true, because on Windows, there's a bonus feature, which is the final part of my sharing, which is the repair feature. So Windows offers the opportunity for you to repair broken software because the software breaks often. They actually store all the installation files in this installer folder. So this installer folder is usually not visible. As you can see, there's no installer folder here. You have to trust me because I'm not trying to hide it or anything. But if you navigate to it directly, so to see Windows installer, you can see a bunch of MSI files stored in the folder directory, and all the MSI files are there. So you may be thinking, if I just, and the interesting part about this installer file is that it's always visible, in the sense that no matter whether you're a low privilege user or a high privilege user, anyone can see this, anyone can double click on it. So if you're a low privilege user, maybe the first thing you think about is, hey, maybe I can try to uninstall some software by double clicking on it. So if you decide to double click on it, it will present you with options to repair or remove the application. You're thinking, hey, if I can just remove the application, then they're screwed. So I'm just going to remove it. But turns out this is fake news, because it tells you that, hey, you need to escalate your privileges to become an administrator before you remove. So seems like this is the end of the presentation, but it's not. Can we do better than this? And the answer is yes, we can. So what can we actually do here? There is a secret command sort of attributed to Sandbox Escaper for finding that. And essentially, you can force a repair as an unprivileged user using this command. So executing the MSI, FH just forced the repair without interactive prompt. So the first thing that this gives you is an ability to script the repair. So for example, if you're trying to hit some time of check to time of use or race condition vulnerability, this is something that you can script and then try to exploit. The second more interesting property about this is that as a low privilege user, if you try to run this and then you use process monitor to look at what's happening. Of course, I tried to run this on a .NET Core or .NET Core installer. And what you see is, of course, a lot of things happening, but the user is actually anti-authority system. So as a low privileged user, by forcing a repair on the MSI file, you are able to run as anti-authority system. That's if you're running from the installer folder. So imagine if you have a rogue installer there, then you're pretty much screwed. But you don't actually need a rogue installer there because most of the time people don't know what's happening in the installer and they code some insane stuff there. So in this example, there is a local privilege escalation in Snaglt, which is a screen recording application. So what is happening in this application is that when you repair it, it actually changes the permissions of some files in the system, which are in a world writable directory. So for example, it's one of the files that is in their folders. And by invoking a repair, it gives everyone access to that file, meaning anyone can read to the file, anyone can write to the file. And obviously that's bad, right? So what you can do in this case is that you first invoke a repair on that file. So you first invoke a repair on Snaglt, and so that file that it sets to allow everyone access can now be changed, right? Then you change that particular file, you replace it with a hard link that actually points to a privileged file. For example, the host file on the Windows system. Of course, then you invoke the repair again, and it allows everyone to change and read the host file, for example. But that's not very useful, right? If you change the host file, nothing really happens. So you want to do something else instead. You want to point it to a DLL, for example, of a driver. So maybe you change the file with a hard link that points to a DLL. In this case, one natural choice would be Microsoft XPS document writer, or printer, which no one actually uses except to do LPE. So if you modify print config.dll of that particular driver, what actually happens is that you can change that DLL, and then that goes back to the original part of our presentation where we did DLL hijacking. By changing that DLL to a malicious DLL, we can do DLL hijacking when we send a print job to the XPS document writer, and then we get privilege escalation. So that's the whole chain. And yeah, so this is pretty insane because repairing as a low privilege user is unheard of, but it's a part of the Windows operating system. So good for everyone. So quick summary of what we went through today. Installation is a really hard thing. It's a very complicated process that no one really understands how to the entire how it fully works. We also talked about DLL hijacking and the initial part of the installation process when we run the installer. And we also looked at each of the different stages of the application lifecycle, right? It's not just the installation, the updating of the software is also an installation, and that you have to be extremely careful about. Uninstalling the software is a privileged operation that you need to be careful about. Repairing the software is something that most people don't even think about, but it's a part of the application. And it can definitely come and bite you when you don't ignore it. And finally, the real important part is that file permissions, especially when you're operating with privileged applications, becomes really hard. And to get it right every single time making sure that there's no sort of time of check to time of use vulnerability, that is extremely difficult. And some things to think about for this after this talk is, of course, we only talk about installers here, but any kind of privileged application is really vulnerable to these classes of vulnerabilities, right? We talk about SUID programs that run as root, or if you talk about root-owned long-running processes, all of these are very privileged applications. They definitely need to touch the file system. They definitely need to write logs. Those are things that you can look out for file system monitoring. And how would you actually fix writing to a temporary directory and to prevent like this kind of race conditions? That's actually non-trivial. And how would you programmatically detect and prevent these classes of bugs? Well, again, not very easy to solve. And this is the end of my presentation. I guess right on time, and I'm open to questions.